if it is minimal, the contractor, minimal, will return that. The enveloping box, the hull of the intersection. It is idempotent if, when I apply twice, I obtain the same as if I apply once. Twice or once, it's the same. So when it is minimal, it is idempotent. So it is important to give you the properties because it makes it possible to understand better what is a contractor, but also, as we will see later, to compute a monotonic and thin contractors it's not different. I can intersect the contractor, make the union, compose them, repeat them, but I will go directly to how I build contractors. So, first I will start with an exercise. The exercise is the following. The idea is to replace all equations by contractors. So let me take a very simple equation. And the simple equation is Z equal X plus 1. Now, each variable belongs to a domain. This is the domain for X, for Y, for Z. I would like to find the domain, so to contract this interval with respect to this equation. So what I want to say is that this equation, I will transform it into a contractor. So how can I use this equation to contract X, Y, and Z? So what can I conclude on X? X belongs to, how can I contract this interval? So tell me. You have an idea? I would like to contract X to be consistent with all the
negative minus 81.
So it is. So how can I? First, I will compute. X is equal to Z minus Y. So X belongs to minus infinity 5. Of course, it was written here. But it also belongs to the domain for Z, 6 infinity, minus the domain for Y, minus infinity 4. You understand this? Now, this is equal to 6 infinity plus 4 minus 4 infinity. This is equal to 2 infinity. I do the intersection and I obtain 2, 5. Okay. So I was able to find a contraction for X. I can do the same for Y, but also for Z. For Z, it's easy. You just have to add this interval with this interval. Okay. And I obtain, okay, so that was a, for X, I obtain 2, 5. For Z, I can obtain 6, 9. And for Y, 1, 5. So, with this method, I was able to transform this equation into a contractor. So all equations will be replaced by contractors. It was what we call a primitive equation because we have a set of equations that cannot be decomposed. This is one of them. So, what I did, I have an equation which is an elementary equation, a primitive equation, and I will call it this equation plus, it is a constraint plus, and I will transform this equation into this algorithm. This algorithm will contract Z to X and Y. And the way I have contracted X is explained here. But you can imagine that it's possible also to contract Z and Y. Okay? This is a contractor. I will call it P plus. Okay? I can do the same for this primitive equation. I can transform this primitive equation into a contractor. This contractor is minimal. It is monotonic, it is thin, and so on. But I have another contractor. So I will have some kind of catalog of contractors that will be combined, and we will see how they will be combined. If I have another primitive equation, like this one, I can also contract optimally X and Y with respect to this equation. So if I draw a picture of what represents, I have X and Y. I have an equation. I have a domain for X, a domain for Y, X, Y, the contractor, give me this. The contractor is given by this algorithm. And I can do this with all primitive equations I have. Primitive equation is an equation that cannot be decomposed. Okay. For instance, here I have a primitive equation. The corresponding contractor is represented graphically here. Before, I will contract first with respect to x2, and then to x1. So there is two steps. Two steps. The first one, you can see, I contract x2. We call it forward, because x1 will contract x2, and x2 will contract backward x1. Backward. Okay? So, from this, up, I have the optimal contractor. This has been, there is some kind of libraries, like IBEX, for instance, a library for contractor, which perform all this contraction. It's very long to, it takes a lot of time just to implement the contraction for the side function. Now I will give you, maybe, excuse me, I will give you a simple example of how it works. I want to solve these two equations with what we call a constraints propagation. So how can I do it with contractors? How can I do it? First, I have two equations. I will replace my two equations by two contractors. The first contractor, given here, is associated to this equation. This contractor is associated to this equation. So I will replace these two equations by two contractors. First. Now I will forget the equation. I will only deal with the contractors. Let me explain. I have my two equations. I have the initial blocks. I will take first the parabola, and I will apply the first contractor. The first contractor, remove the gray part. Then I will apply the second contractor. And then I will come back to the first one, and to the second, and to the first one, and so on. And I will converge in a polynomial time. So here we don't see the difference because we have only two variables, but the process can work even if I work with thousands of variables. Then, of course, here I have two solutions, here and here. So I can bisect. Normally we are not supposed to bisect, but I can bisect. And I will start again the contraction process here and here. And with only one bisection, I was able to find two solutions. But you should remember that for high-dimensional problems, the number of bisections is exponential. The number is exponential with respect to the number of variables, and the number of contraction is linear with respect to the number of variables. So here we will see the difference. Yes?
But it looks like as though it's put a number by bisecting.
Sorry.
It looks, the diagram there looks like as though there are a number of bisections.
No, there is no bisection.
Okay.
Here there is only contraction. Look. Here, this is a contractor associated with the parabola. This is the contractor associated with this. So this one is optimal. This one is optimal, but C1 or C2 is not optimal. You understand why?
So you might say.
No. Look, here I have C1, C2 of C1. It is not optimal because it is not idempotent. The set associated with C1 is the parabola. The set associated with C2 is this one. The set associated with C1 or C2 is this point and this point. It is the intersection of the two constraints. As you can see, C1 or C2 is not optimal because if I apply it once more, C1 and C2, so what we can see here is C1 or C2 squared twice. So here is C1, here is C1 or C2. Okay? Here is C1 or C2 squared. Here is C1 or C2 power infinity. Fixed point. You understand?
So it looks like you're trying to say that C1 and C2 are looking optimal if the sizes are equal when you try to contract it towards the intersection of C1 and C2.
So,
I mean, the first time when you said C1 is not optimal with respect to C2 was the sizes were different, I guess.
yes.
The contraction sizes.
So
when they were approaching towards that intersection.
yes. Well, so what you want to say? It's your question or an affirmation?
I'm trying to ask a question. I'm not trying to understand that.
Okay. So what is your question? Is
how the C1 and C2 is not optimal?
okay. Because the set associated with C1 and C2. So what I did not define because I tried to go fast, but maybe too fast. What is the set associated with the contractor? The set associated with the contractor is, whoops. Okay. So if I give you the contractor, I give you a box, you can test it. You take a box, the contractor will give you that. If I take a point, I test the contractor, empty set. If I take this point, I test it, I contract, no contraction. It means that I will define the set X, the set of all X, such that the contraction of the box, the singleton X, is equal to X. Okay, he defined me a set. here for C1 or C2, if I take any point here, here, or here, it will be contracted to the empty set. If I take this one or this one, they will not be contracted. So it means that the set associated with the contractor C1 or C2 is made with 2 points. You understand what I mean? So it is optimal if, imagine I take a set X. It is optimal if it is the smallest one which is possible. So if X is made with 2 points, it will be optimal. Okay, if I have, sorry. So assume that my set here is made with 2 points. An optimal contractor will be like this one. If I take this box, I will contract like this. If I take this box, it will contract like this. If I take this box, it will contract like this. Okay. Okay, you understand? So, now let me come back to it's time because I said 2 hours, but I will continue tomorrow. Don't worry. So now, because it takes some time to continue, but I suggest if you have some question, I'm still here. You can ask me question. If you want to know more about application and contractor, which is important, because let me recall you that actual application should be solved more and more in a distributed way, and we do not have only few equations, we have most of the time thousands of equations that could be solved globally by several agents. And it can only be done using a contractor approach. So what else? So I stay here if you want to ask me any question, and I come back, of course, tomorrow for the next lesson. Yes.
Where can you find the presentations available?
Yes, they are on my website. There is all videos also available on my website. So maybe what I could do is to give to Alexandro everything. Yeah. And also the videos, all links. And I suggest that Alexandro send to all labs, it's possible?
To the software.
The link so that everybody will.
Yes.
Okay?
Yes.
And also, if you want to implement on your computer, all source code are also available. Since I'm here for the week, you can come with a computer. I can install C++, IBEX, for instance, if you want to implement it. It's not difficult, but if I'm here, it's much more easy.
Thank you very much.
Thank you.